For his astounding commitments to the fields of material science, Michio Kaku has really mentioned that the James Webb Space Telescope has seen 6 immense plans that experts acknowledged were unequipped for existing. These evaluations have the validity to open up new perspectives on the way in which we could unravel the universe. The straightforwardness is both dazzling and modestly testing existing speculations about the new developments and improvement of universes. It suggests an incredible arrangement to pay extraordinary regard for these updates, and the certification by such trained professionals highlights the significance of these disclosures. Kaku is a surprising figure in the scientific field, a physicist of American and Japanese legacy. He is seen as an expert in both ordinary material science and quantum mechanics. Rather than some more moderate and precarious themes, experts like Kaku have been available to the amazing, prideful potential outcomes of the James Webb Space Telescope mission. His energy to embrace new discoveries and share them with the public shows his obligation to propelling our comprehension of how we could decipher the universe. We are appreciative that this unmistakable master has chosen to end his quietness and straightforwardly share what can no longer be denied. The powerful, clear tone of the remarkable physicist is clear in his remarks on the disclosures made by the James Webb Space Telescope, giving the possibility that this has been an advancement that has reignited his interest. Join us as we investigate the repercussions of Kaku's reception of these 6 titanic plans. Kaku is a master who has consistently had the limit to contemplate new theories throughout his life. He has shown a responsiveness to thoughts that challenge ordinary thinking, figuring out that Einstein's hypotheses of relativity and Newton's regulations, while basic, are restricted in completely grasping the universe's complicated plan. Kaku accepts that the disclosures of the new telescope could push the area of cosmology. Anyway, a large number of his partners still can't embrace this view. This has caused concern and misgiving among Big Bang researchers and pundits of quantum mechanics. However, this only draws laughter from Kaku. The James Webb Space Telescope has uncovered 6 huge universes tracing all the way back to the earliest seasons of the universe. Every one of these huge frameworks contains more stars than our own Milky Way, despite having formed simply 200 to 700 million years after the Big Bang. The group of cosmologists who made the discovery has named these brilliant, vast frameworks universe breakers. If confirmed, they would fundamentally change how we figure out the universe. The aftereffect of these disclosures is significant, suggesting that the universe's early years were undeniably more dynamic and complex than recently thought. The hypothesis of how things began lets us know that the universe was turbulent after the Big Bang. The main solid objects took a long time to form, and it took significantly longer for these objects to reach adequate thickness and produce light. The advancement of complicated structures like universes was remembered to have occurred much later. A portion of the recently found tremendous frameworks beat the Milky Way in size, and their massive splendor suggests they were likely forming many new stars each year. While our universe forms stars sporadically, it remains hazy precisely at what point the first structures formed, and scientists have not yet settled this. One thing is clear. At the start, there might have been only individual stars or gatherings of stars that eventually coalesced into larger designs over time. More modest frameworks supported bigger, more monstrous designs. Beforehand, it was trusted that such enormous and complex frameworks were unequipped for existing at that time, which raises the question of whether the universe is much older than recently acknowledged or if such huge frameworks formed much sooner than guessed. This situation is troublesome to accommodate with customary science, which still finds issues with this model. A few areas of material science have explicitly excused these revelations and scrutinized the accuracy of age estimates. Kaku is aware of this and had this to say: "There are various models and obsolete hypotheses that endure due to the influence of certain well-educated specialists. Many of these hypotheses were experimentally exposed when essential examination revealed their flaws. Reality in any science, particularly in material science, lies with the work of experimentalists who keep the hypotheses sharp and on track." He went on, "Here on Earth, we have very little information about the genuine beginnings of the universe. This explanation highlights the importance of constant testing, refreshing, and reaffirming in the scientific process. The hypothesis of how things came to be was first illustrated in 1927, based on observations of the universe's expansion. This data led to the conclusion that the universe began from a single, boundlessly thick point and has been expanding ever since. At the time, it was hard for people and researchers to envision a universe with both a start and an end. The plausibility of an immortal universe was outside human ability to grasp. Even today, scientists still struggle to fully grasp it. However, it is vital to consider these possibilities, regardless of whether the new discoveries align with what specialists have acknowledged for a long time regarding the theory of how things began. Science has shown repeatedly that reassessment and openness to historic ideas are crucial to the scientific process. For example, when Einstein was young, it was once believed that stars and planets were fixed in the universe and that these specific arrangements occupied a defined space. But now we know that everything in the universe is moving. Planets orbit stars, and stars move within their systems at speeds of several kilometers per second. Entire universes move quickly through the universe, whose ultimate destiny we still can't predict. This astounding understanding of the universe challenges long-held beliefs and highlights the need for continuous inquiry and change in our scientific thinking today. Researchers are challenged to recognize irregularities and discover that speculations are inadequate until they have been thoroughly tested or confirmed by observational data. The possibility of the Big Bang emerged from the observation that universes are getting away from one another, and this distance is proportional to their separation from Earth. This understanding, known as Hubble's law, proposed that the universe was expanding over time. Factors like cosmic microwave background radiation and the redshift of light from far-off worlds, along with other cosmological patterns, seem to support this theory. However, it is important to remember that before, people who believed the Earth was flat and that the Sun revolved around us also had observational proof for their convictions, until new events or technological advancements came along that provided a clearer picture. Right now, we are seeing a similar situation. Scientists anticipated the new James Webb Space Telescope to confirm questions related to the theory of how things became, but instead, they may have countered these 6 colossal frameworks that seemed impossible. This shows that science is constantly advancing, and researchers must stay open to new discoveries and reconsider existing theories, considering the available evidence. The shocking revelations have tested current understanding and provoked a reassessment of well-established cosmological hypotheses. Scientists use redshift as a tool to calculate various measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as light sources and observers move relative to one another. To understand this, imagine stopping and hearing a car moving toward you. As the vehicle gets closer, the sound gets louder, but when the vehicle passes or moves away, the sound changes. This happens because the sound waves change as the vehicle moves. The same is true for light. When a light source like a distant star approaches us, the light shifts to bluer tones. On the other hand, when the light source moves away, the light shifts to redder tones. This phenomenon is called redshift. Physicists have converted redshift values into rates and distances for measurements in the study of the universe. However, it is important to note that even a small mistake in these measurements can have significant consequences. The previous estimation methods are now under review. The latest discoveries related to our universe require consideration of whether they are genuinely based on redshift errors or if some scientists are simply dismissing current facts. This is a question that requires careful assessment and a thorough review of the data and methods used in the research. The ongoing assessment and reassessment of measurement methods highlight the growing understanding of continuous inquiry. Thank you for watching the video. As always, we remind you to post your requests in the comments section. If you enjoyed the video, please hit the like button and share it so it reaches more people. Also, subscribe to the feed so you don't miss more content like this. Thank you again for watching, and we'll see you in the next one. This call to action encourages viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific discussions. The exploration of our universe, with its vast distances and complex bodies, continues to amaze and challenge scientists worldwide. From early hypotheses about the universe to the latest discoveries made possible by cutting-edge technology, discovery reshapes how we might interpret the universe and extends the limits of human knowledge. One of the most significant and enduring questions in cosmology revolves around the origin and development of galaxies. Galaxies are like vast cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is crucial not only for unraveling the mysteries of our universe but also for testing or confirming existing theories. For instance, the Big Bang theory, proposed almost 100 years ago, suggests that the universe began from a single, infinitely dense point and has been expanding ever since. This idea arose from observations of the universe's expansion and the cosmic microwave background radiation, considered remnants of the early universe's tremendous energy and light. However, recent discoveries, especially those made by the James Webb Space Telescope, JWST, have challenged some key ideas central to the theory of how things came to be. The JWST, with its remarkable sensitivity and resolution, has identified galaxies that appear far larger and more developed for their age. One such discovery includes 6 massive galaxies dating back to when the universe was only 200 to 700 million years old, a mere flash in its 13.8 billion-year history. These galaxies, named universe breakers by the research team, challenge traditional thinking as they are already so large and bright at such an early cosmic age. The discovery of these galaxies raises intriguing questions about the rapid development of the early universe and challenges existing models of galaxy formation. According to prevailing theories, galaxies form slowly over billions of years through the merging of smaller systems and the accumulation of gas and stars. The presence of these massive galaxies so early in cosmic history suggests a far more complex and potentially faster process of galaxy formation than previously thought. Furthermore, the discovery highlights the pivotal role of technological advancements in reshaping how we understand the universe. The JWST's ability to peer deeper into space and capture faint light from distant galaxies has allowed astronomers to uncover previously invisible pieces of the universe's early development. These insights provide valuable clues about the conditions and processes that governed galaxy formation during the universe's infancy. The implications of these revelations extend beyond cosmology. They challenge scientists to revisit and refine existing cosmological models to better account for the observed diversity and complexity of galaxies across vast timescales. They also highlight the dynamic and evolving nature of scientific knowledge, where new discoveries can spark future breakthroughs and open new avenues for research. As researchers continue to analyze and interpret the data from the JWST and other observatories, the study of galaxy formation remains an exciting and rapidly advancing field. Each new discovery brings us closer to unraveling the mysteries of our origins and helps us understand the fundamental processes that have shaped the universe as we know it today.